Noche Cósmica.
On a clear night, when the sky opens above you in its full dark abundance, you might wonder if those distant points of light, the ones that have traveled so far to reach your eyes, have ever wondered about us in return. That photon from Sirius, burning toward Earth for more than 8 years through the vacuum of space, arriving tonight in your field of vision, did its journey have a purpose beyond accident? Or is the universe simply scattering light in all directions, asking no permission, expecting no recognition? This is one of the oldest puzzles that has ever kept a human being awake. Not the question of whether we will reach the stars, but something deeper, something that has no clear answer yet, despite all our science. How is it that we can see the stars so vividly, feel their presence so keenly across the gulf of space, and yet remain so profoundly separated from them? What is it about the cosmos that permits us to perceive our neighbors so clearly, while making them forever untouchable? The light arrives, the distance persists. If you've found yourself drawn to that mystery, to the ache of reaching towards something beautiful and distant, knowing that the very laws of physics might conspire against your arrival, then this exploration is meant for you. If you'd like to drift through the deeper architecture of why we may never reach another star, despite every dream and calculation we've ever devoted to the question, I invite you to subscribe. We'll journey together through the silence between worlds. For now, imagine yourself in that darkness, not the artificial night of a city, where streetlights and screens dilute the stars into insignificance, but a true darkness, the kind that existed before electricity, before glass domes and artificial light, a darkness that still exists in pockets across the world, waiting for those patient enough to find it. It is in such moments, when your eyes have adjusted and the pupils have expanded wide, that you can perceive what the ancients perceived, not with instruments, not with mathematics, simply with the naked human capacity to see. The starlight itself is a kind of silence. It falls without sound. It travels through the absolute vacuum of space, a place so empty that between the stars you might pass through cubic miles and encounter fewer atoms than exist in a single breath of air. And yet that emptiness carries something. It carries light that departed before your great-grandmother was born. In some cases, before your civilization began. In the most distant cases, before your species existed at all. Consider what this means. The photons that enter your eye on a winter evening have been traveling, unimpeded, through the void for 4 years, 8 years, 13 years, 43 years. They have passed through solar systems you will never name, through regions of space where no human telescope has yet been directed. They have survived radiation. They have been bent by gravity itself, their paths curved by the mass of distant galaxies. And still they arrive, patient, relentless, asking nothing. This is the strange geometry of the night sky. It is not actually the present sky you are observing. It is a photograph of the past, written in waves of light. When you look at the star Betelgeuse, you are seeing it not as it is, but as it was over 600 years ago. The photon you receive tonight was emitted when your ancestor walked the earth, lived a life, loved, struggled, and passed into history. The star itself may have changed in the centuries since. It may have shifted its position, grown brighter or dimmer, even exploded in a supernova whose light has not yet reached Earth. But you cannot know this. You see only the ancient message. The light carries information. It carries time. And in this fact lies something both beautiful and unsettling. Your connection to the distant stars is not a connection in the present moment. It is a connection stretched across time and space in equal measure. The universe permits you to see across the light years, but only by condemning you to observe what was, never what is. It is a form of cosmic distance that operates in 2 dimensions at once, the distance of space and the distance of time. Somewhere out there beyond the pinpricks of visible starlight, beyond what your unaided eye can perceive, orbits a star around which another world might turn. There might be oceans. There might be something watching the night sky of its own world, seeing light from Earth, perhaps wondering about us in return. But the message from that world, if a message exists, has not yet reached you. It is traveling at the only speed light permits, the speed of light. It is moving at 186,000 miles per second, and still, at that speed, it might require hundreds of years to complete its journey. This is the first truth that will accompany you through this exploration. The stars are not silent because space is empty. They are silent because communication itself requires time, and time is the medium through which all distance must be crossed. A year is not simply a measure of Earth's orbit around the Sun. It is also a measure of how far light can travel. The light year is both a unit of distance and a unit of duration. The two are inseparable. In the darkness of night, if you remain patient, if you let your eyes adjust and your mind grow quiet, you may begin to sense this peculiar truth. The stars are not points of light suspended in an eternal present. They are messages from the past, traveling toward a future in which you may no longer exist. They are time made visible, distance made palpable. And the question that emerges from this realization is as old as wonder itself. If we can see across such vast expanses of space and time, why is there an almost cruel barrier between observation and arrival? The ancient astronomers did not know about light years. They did not know about the speed of light or the vast distances that separated one star from another. But they knew something. They knew that the stars were far. They could sense it. There was a loneliness in that distance, a kind of sublime ache that arose from perceiving something beautiful that seemed beyond reach. That ache has not diminished with our science. If anything, it has deepened. Now we know exactly how far the stars are. We know the numbers. We have calculated the barrier to the millimeter, and the barrier remains. On this night, as you drift deeper into thought, consider what it means that the nearest star to Earth, Alpha Centauri, which is only 4.37 light-years away, is so distant that the light leaving it right now will not reach us until you are long gone. Centuries will pass. Civilizations will rise and fall. The light will continue its journey, indifferent to human history. And when it finally arrives in the year that you might imagine as the far future, it will carry a message from a past so ancient that everything you knew will have transformed into unrecognizable shapes. The silence of space is not empty. It is full of these messages, full of these journeys, full of light carrying time itself across distances that have no meaning in human terms. And somewhere in that silence, there may be a barrier, not a wall, not something physical that blocks the way, but something subtler, something written into the laws of physics themselves, something that asks the question, is it possible that we were never meant to arrive? The question that draws us ever outward, across the centuries and through countless generations of human wondering, is deceptively simple. What lies beyond the next star? And more urgently, could we ever truly go there? These are not merely the idle fantasies of dreamers and science fiction writers, though they are certainly that too. They are questions that have begun to reshape how we understand the very limits of what might be possible for our kind, and they lead us into one of the most profound conversations humanity can have about itself, about time, about energy, about the price we might be willing to pay for knowledge that lives forever beyond our grasp. If you've ever felt the pull of wondering what waits in the deep black between worlds, if the mathematics of impossible distances has ever sparked something in you, if you've found yourself asking whether the stars are truly meant to be unreachable or merely to remain unconquered for now, if any of these questions has nestled into the quiet corner of your mind where curiosity lives, then I invite you to subscribe to this channel. What unfolds here is not a simple tale of we will or we cannot. It is something far more intricate. It is a meditation on the gap between human desire and physical law, between the dreams we've carried since we first looked up into the darkness, and the stubborn, magnificent refusal of the universe to make the journey easy. Over the coming minutes, we will walk through the reasoning, the calculations, the ingenious proposals, and their inevitable constraints that together compose an answer to why the nearest star might remain forever beyond our fingertips, even as we grow cleverer, wealthier, and more determined with each passing year. The distances involved in this question are so vast that they shatter the human intuition almost immediately. We speak of them in terms that have become almost casual in our age: light years, parsecs, the void between solar systems, and yet each of these measurements represents a gulf so profound that to truly grasp it is to feel a peculiar vertigo. But there is something oddly beautiful in that feeling, is there not? The sensation of confronting something so much larger than ourselves, so indifferent to our yearnings, yet so mesmerizing that we cannot look away. That beauty, that pull, is part of what makes this inquiry so worthy of patience and attention. For what we discover about why the stars may remain forever distant will teach us something equally important about ourselves, about the nature of ambition, about the boundaries of possibility, about what it means to be a species forever gazing upward and wondering. The path we are about to trace together is both scientific and philosophical. It moves through the hard mathematics of propulsion and energy, through the elegant but unforgiving constraints of Einstein's relativity, through the countless engineering challenges that separate concept from reality. But it also invites us to imagine, to wonder what the first human ship to leave the solar system might have looked like, to ponder the minds of the people aboard it, watching their home star fade to just another point of light in an ocean of points of light, to sit with the question of whether consciousness itself might one day leave its cradle and wander the cosmos in forms we cannot yet imagine. These questions are not frivolous. They are at the very heart of what it means to be human, what it means to dream, what it means to reach towards something we may never touch. The journey of understanding will ask you to hold multiple truths at once. Yes, there are genuine physical laws that appear to place interstellar travel far beyond our current capabilities. Yes, the energy requirements are staggering, the timescales are crushing, the technological hurdles seem almost cartoonishly insurmountable. And yet, we are creatures who have solved problems that once seemed equally impossible. We have learned to split the atom, to map the genetic code, to send machines to the edge of the solar system and have them still speak to us across the void. Perhaps the question is not whether we will reach the stars, but what we will become in the process of trying, what sacrifices we might make, what new forms of existence we might have to invent, what patience we might have to learn. As we move deeper into this exploration, you will encounter ideas that range from the rigorously established to the thoughtfully speculative. Some of what we will discuss has been proven by decades of research and calculation. Other concepts remain beautiful possibilities, things that our greatest minds believe might be achievable, but that have never been tested, never been constructed, never been proven to work at the scale we would require. That is the nature of this inquiry. We are standing at the edge of what we know and looking out into what we might imagine. And that edge is a fascinating place to linger. It is where human ingenuity meets cosmic indifference. It is where our dreams meet the law of physics and must negotiate with it, bargain with it, sometimes surrender to it entirely. So settle into this with us. Not with the expectation of easy answers, but with the openness to let your mind wander through vast distances and strange scenarios. Let yourself feel the weight of astronomical numbers. Let yourself wonder. Let yourself sit in the beautiful tension between what we want to achieve and what the universe will allow. This is a conversation that will wind through multiple pathways of thought, that will ask you to hold paradox and possibility in equal measure, that will ultimately offer not a definitive answer, but something perhaps more valuable, a deeper appreciation for why the question matters at all, and what our continued asking of it reveals about the species asking. There is a spacecraft that has been traveling for longer than most people alive today have walked the Earth. The Voyager 1 probe left our world in 1977, carrying with it a golden record of human sounds and music, intended as a message to whoever or whatever might find it in the darkness. For nearly 50 years, it has been moving through space at approximately 37,000 miles per hour, which is faster than anything you have ever experienced, faster than you could even imagine standing still. It is still accelerating away from us, still climbing outward through the void, driven by the momentum imparted to it decades ago when it slingshot past Jupiter and Saturn. And yet, despite this staggering velocity, despite nearly 5 decades of relentless motion, Voyager 1 has traveled only about 14 billion miles from the place where it began. 14 billion miles. Say those numbers aloud to yourself in the stillness of the night. It is a distance so large that light itself, the fastest thing we know, requires more than 20 hours to cross it. Light that left our sun when your great-grandparents were children has only recently caught up with Voyager 1 in its cosmic race. Yet this achievement, 50 years of travel across what most of us would call an incomprehensible distance, represents barely a whisper of motion when measured against the true scale of the stars themselves. Now consider this. The nearest star to our Sun, a small, dim red star called Proxima Centauri, dwells at a distance of 4.24 light-years. A light-year, you may remember, is the distance that light travels through the vacuum of space in a single year. It is not a measure of time, though the confusion between those two ideas is natural and almost universal. It is a measure of distance, a truly enormous measure of distance. The distance that light, the fastest thing in the universe, covers in 365 days of uninterrupted motion. If you were standing on Proxima Centauri, looking back toward our Sun, your gaze would take 4 years and some months to complete the journey home. How long, then, would it take Voyager 1 to reach that star? The mathematics are not complicated, though the answer is almost numbing in its coldness. At its present speed, Voyager 1 would require approximately 73,000 years to traverse that single light-year distance separating us from Proxima Centauri. 73,000 years. That is longer than the entirety of human written history. It is longer than the span from the invention of agriculture to this present moment. It is longer than the last ice age. When Voyager 1 launched, the Great Pyramids of Egypt had already stood for more than 2,000 years, monuments built by human hands that we regard as ancient beyond reckoning. Yet they are newcomers to the span of time Voyager 1 would require to cover a single light-year of space. And Proxima Centauri is merely the nearest. It is our cosmic neighbor, our closest stellar companion, in an unimaginably vast neighborhood. If we extend our gaze only slightly further, to the stars visible in the winter sky, the next nearest stellar system lies 4.4 light-years distant. Then 5 light-years, then 6. The stars you see on a clear night, those pale pinpricks of ancient light that have captivated human imagination since the dawn of consciousness, are not scattered throughout space like islands in a vast ocean. They are separated by gulfs so profound that even light, the very substance of speed itself, requires years to cross them. And Voyager 1, fastest of all our creations, would take centuries to reach most of them. There is something almost poignant in this knowledge. We have built a machine that is faster than anything in our daily experience, faster than a jet, faster than a rocket, faster than escape velocity itself, We have aimed it at the stars. We have sent it sailing outward with our music and images and greetings carved into gold, our hopeful message to the cosmos. And still, the distance defeats it so completely that the word failure seems inadequate. It is not that Voyager 1 cannot reach the stars. It is that the stars are so far away that cannot becomes almost meaningless. The distance is not a problem to be solved. It is simply the way the universe is made. Yet perhaps there is comfort in this too. We have not stopped trying. Even as Voyager 1 sails outward on its centuries-long journey to nowhere in particular, we remain on Earth, thinking, imagining, asking ourselves the question that has never truly left the human mind. How might we cross these distances? How might we overcome not merely the speed of our vessels, but the fundamental geometry of space itself? If we could not go at Voyager 1's speed, then might we go faster still? And if we could go faster, how much faster would we need to travel to make the journey across a light year into something measured in decades rather than millennia? What would it cost us? What would we have to become? These are the questions that have grown from the soil of our starfaring ambitions, and they lead us away from the comfort of what we know and toward the strange territories where physics itself becomes difficult to comprehend. The desire to slip beyond the boundaries of Earth did not begin with rockets or telescopes or the rational calculations of physicists. It lived first in the human imagination, in the stories we told ourselves when the night sky was all we had to contemplate. Long before we understood that stars were suns, before we even knew their true distance, ancient peoples gazed upward and wove tales of wandering souls, of spirits released from earthly binds, who could traverse the heavens freely, moving from star to star as easily as we might walk from room to room. The Greeks imagined Charon ferrying souls across rivers toward the underworld, but they also whispered of Icarus, of wings fashioned from feathers and wax, of the hubris and longing tangled together in one desperate flight toward the sun. What was this mythological language but humanity's oldest dream of escape, of transcendence, of reaching places that felt impossible, yet somehow necessary? In the sacred texts of many cultures, heaven itself was understood as a place one might journey to, beyond the clouds, beyond the visible world. The medieval cosmologies that map the structure of the universe often depict a voyager moving through concentric spheres, through layers of reality, traversing distance not through physical means, but through spiritual transformation. There is something profoundly moving in recognizing that across centuries and continents, human beings felt the same pull toward the distant heavens. They did not have the language of physics or engineering, but they had the language of myth, and through myth they rehearsed, again and again, the possibilities of leaving home and reaching for something impossibly far away. When written science began to emerge in earnest during the Renaissance, the mathematical mind started to wrestle with what the mythological mind had always intuited. Johannes Kepler, the German astronomer and mathematician who lived in the early 17th century, did something remarkable. He wrote what many scholars consider the first genuine science fiction story. It was called The Somnium, The Dream, and in it, Kepler imagined a journey to the moon. Not a physical journey, mind you, not yet, but an imagined one, a dream narrative told with such attention to astronomical detail, to the mathematics of orbital mechanics, that it felt almost plausible. The protagonist travels through the void, experiences weightlessness, observes how celestial mechanics might work from a perspective beyond Earth. Kepler was writing fiction, yes, but he was doing something even more ambitious. He was practicing, in his imagination, the possibility of space travel before the technology existed to make it real. The 18th and 19th centuries brought an explosion of such imaginings. As telescopes grew more powerful and showed us increasingly distant worlds, As the Earth's own size and place in the cosmos became clearer through measurement and observation, writers began to populate the spaces between worlds with narratives of human aspiration. Jules Verne, that magnificent engineer of the imagination, wrote From the Earth to the Moon in 1865, describing a projectile launched from a cannon in Florida that would carry humans to the lunar surface. The technical details were wrong, of course. A cannon could never generate the precise conditions needed for safe space travel, but the underlying logic was sound. Verne understood trajectories, gravitational forces, and the basic physics that would eventually govern space travel. He was not simply fantasizing, he was extrapolating from the science he knew, pushing it forward into a future he could not see, but could imagine with remarkable clarity. What strikes a listener now, centuries later, is how these early visions were animated by a particular kind of hope. The starship in these stories, whether imagined by Kepler or Verne or later by H.G. Wells, was not primarily a vehicle designed to escape some catastrophe or to exploit resources. It was, at its heart, an expression of human curiosity, of the conviction that we had a right to know what lay beyond. The starship was humanity's way of saying, I wish to see, to understand, to stand upon other worlds and breathe unfamiliar air. There was something almost innocent in that impulse, though we might not use that word now. The early 20th century saw the birth of what we now call science fiction as a distinct literary form, and with it came far more detailed imaginings of space travel. In Russia, Konstantin Tsiolkovsky, a schoolteacher who was largely self-taught in mathematics and physics, began in the 1880s and continuing into the new century to develop the theoretical foundations of rocket propulsion. He published widely in Russian scientific journals, and though his work was not widely known in the West until much later, he was working through, on paper, in the realm of pure mathematics, the actual physics that would be needed to escape the Earth. Tsiolkovsky understood something crucial. A vehicle designed to reach space would need to be powered by controlled explosions, by the chemical reaction of fuel and oxidizer released in carefully managed bursts. He derived what would later be called the Tsiolkovsky rocket equation, one of the fundamental relationships governing space travel. But even as he worked out these calculations, even as he showed mathematically how escape from Earth was theoretically possible, he was also writing fiction, stories in which his rockets were not merely vehicles but symbols of human aspiration, stepping stones toward the stars. The dreams grew more elaborate through the 20th century as real physics began to collide with imagined futures. In the 1920s and 1930s, as rockets began to be tested and refined by engineers in Germany and elsewhere, a whole literature of space exploration bloomed. The German engineer Hermann Oberth published works of both theory and speculation, developing practical rocket designs while simultaneously publishing novels that depicted human colonies on the Moon and Mars. There was a fluidity between the scientific and the imaginative that now seems almost quaint. Engineers and scientists would publish their theoretical calculations, and then, in the same journal or in adjacent pages, they would present fictional scenarios of journeys between worlds. It was as if the act of imagining itself was part of the scientific process, a way of testing ideas not yet technically feasible, of dreaming forward toward what might be possible. By the middle decades of the 20th century, a particular vision of interstellar travel had crystallized in the science fiction imagination. The starship would be vast, a vessel capable of carrying hundreds or thousands of humans. It would be powered, in the stories at least, by engines far more exotic than chemical rockets, engines that somehow harnessed antimatter, or the power of the atom, or forces not yet discovered. Inside this vessel, the crew would live something approximating a normal life. They would have families, grow food, establish hierarchies and cultures. The ship itself would be a small world, a new Earth sailing through the void, toward a distant destination. There was something deeply comforting in these visions, something that spoke to the human need for continuity, for home. Even as we imagined leaving Earth behind forever, we imagined bringing Earth with us, carrying our homes and our communities into the depths of space. What is perhaps most curious about these early dreams, from a perspective of several decades later, is how they minimized or simply ignored the most fundamental challenges of interstellar travel. The distances were understood intellectually. Everyone knew that the nearest star was more than 4 light-years away, but in the narratives, this distance seemed somehow manageable. A ship would be built, a crew would board, and years or decades later, give or take, they would arrive. The problem was treated as primarily one of engineering and time, not of physics and impossibility. The writers and dreamers of those eras, with all their ingenuity and imagination, had not yet fully grasped how catastrophically difficult the task would prove to be. How many fundamental constraints would emerge once serious attempts were made to translate fantasy into engineering reality. You begin to grasp, then, the true scale of what separates us from the stars. Not merely distance, but something far more fundamental, a law written into the fabric of existence itself, one that Einstein revealed to us over a century ago, and one that we're only now beginning to understand in our bones. Light speed isn't simply the fastest thing we know about. It's the speed limit of the universe. Nothing with mass can reach it. Nothing can exceed it. And this single fact, this elegant, immovable ceiling, may be the deepest reason why the stars will remain forever beyond our grasp. To understand why requires us to sit with an idea that feels almost mystical in its implications. Einstein showed us that space and time are not separate things floating independently around us. They're woven together into something called space-time, and the speed of light is the one constant that threads through all observers everywhere at all times. Light always travels at roughly 186,000 miles per second. Always. Whether you're standing still on Earth or moving through space at tremendous velocity, a beam of light will pass you at that same speed. This seems to defy ordinary intuition. Shouldn't a faster observer see light traveling slower relative to them? But it's been confirmed countless times, and it reshapes everything we believe about motion and energy. Here's the peculiar consequence. As an object accelerates, its mass appears to increase relative to the observer watching it move. This isn't a trick of perspective. It's real. The closer something gets to light speed, the more massive it becomes. And to accelerate something means you have to push on it with force, which means you need energy. More mass requires more force to accelerate further. So as you push a spacecraft closer and closer to light speed, you're fighting against an ever-growing inertia, a resistance to acceleration that becomes steeper and steeper, asymptotically approaching infinity as you approach the speed of light itself. At light speed, the mass would be infinite. An infinite mass requires infinite energy to accelerate. An infinite energy is impossible. Therefore, no object with mass can ever reach light speed. This isn't a limitation of our engineering, though it certainly feels that way. This is a law, as fundamental as gravity, as binding as the second law of thermodynamics. And it means that any journey to the stars will always take time, real time, measured in years or decades or centuries, no matter how close to light speed we manage to push our vessel. Consider what it takes to accelerate something even fractionally close to that cosmic speed. Suppose we want to send a spacecraft to Alpha Centauri, the nearest star system beyond our Sun, at just 10% of light speed. That's a reasonable expectation for something advanced humanity might achieve, perhaps with antimatter propulsion or some form of advanced fusion. But to accelerate a spacecraft of even modest mass, say 1,000 kilograms, roughly the weight of a small car, to 20,000 kilometers per second, requires an extraordinary amount of energy. Picture it in numbers. The kinetic energy of that spacecraft, at 10% light speed, would be on the order of a petajoule. That's a quadrillion joules. The entire world produces about 580 exajoules of energy per year through all sources combined: fossil fuels, nuclear, renewables, everything. A petajoule is 1,000th of an exajoule. So in some sense, accelerating a small spacecraft to 1/10 of light speed would demand energy equivalent to what all humanity uses in roughly 6 hours. Not quite impossible, but daunting. And that's only to 10% of light speed. Now imagine you want to go faster. Imagine you want 30% of light speed, which would mean reaching Alpha Centauri in roughly 40 years rather than 130. The kinetic energy doesn't scale linearly with velocity. It scales with the square of the velocity. So at 30% light speed, you need 9 times more energy than you did for 10%. At 40%, 16 times more. At 50%, 25 times more. The energy demand shoots upward, and the practicality plummets. You're not just fighting against the mass of the spacecraft anymore. You're wrestling with the fabric of space-time itself, with the deep mathematics that says the universe has a speed limit and we're approaching it. And there's another layer to this constraint, one that becomes painfully apparent when you do the calculations. You don't just accelerate once and coast to your destination. If you want to arrive at another star system in any reasonable time frame, you need to decelerate as you approach it. You need to slow down so that you don't simply pass through the system at tremendous velocity, unable to stop, unable to study it, unable to accomplish anything scientific or exploratory. To do that, you need fuel on the other end, or you need to carry enough fuel on your spacecraft to perform both acceleration and deceleration. And fuel has mass. Mass demands more energy to accelerate. The problem feeds on itself. This is the true cruelty of relativistic travel. Approaching light speed demands energy that scales not just with your cargo, but with your fuel itself. And we haven't even touched yet on the cosmic radiation that bathes space between the stars, or the sheer quantity of hydrogen atoms you'd encounter at high velocity, each one a tiny bullet striking your hull. Those hazards will demand shielding, which adds mass, which demands more energy, which means more fuel, which means more mass still. So when we speak of reaching another star, we're speaking of overcoming not merely the geography of space, but the physics of motion itself. We're speaking of harnessing energy on a scale that civilization has never gathered and focused toward a single goal. And we're speaking of doing it with a spaceship, not a magical portal or a wormhole, or any of the speculative shortcuts that physics fiction sometimes imagines. With actual machinery, actual propellant, actual physics that constrains what's possible. It's worth asking yourself, what does this mean? What does it mean to live in a universe where the speed of light is truly inviolable, where energy demands grow so ferociously as you approach that limit? Does it close the door entirely, or does it simply make the journey so forbiddingly expensive that we need to reimagine what kind of journey we're willing to attempt? These are questions that guide the next stage of our thinking about the stars. For hidden within the constraints Einstein revealed, there are also possibilities that emerged from physics itself, proposals from some of the finest minds of our age about how one might, in principle, propel a spacecraft far faster and more efficiently than chemical rockets ever could. Now consider a cold equation that has haunted rocket engineers since the earliest days of spaceflight, a mathematical truth so unforgiving that it reveals why reaching even the nearest star might demand resources we could scarcely imagine gathering. It is the Tsiolkovsky rocket equation, named for a Russian schoolteacher and dreamer who worked it out in the late 1800s. And though it wears the austere face of mathematics, it tells a very human story of desire, meeting resistance. The equation itself appears modest enough on the page, but what it describes is a kind of exponential cruelty. To send a spacecraft to greater and greater speeds, or over longer and longer distances, you do not simply add proportionally more fuel. Instead, the mass of that fuel grows in a way that compounds relentlessly, spiraling upward in ways that become almost incomprehensible. If you wish to double your spacecraft's final velocity, you cannot simply double the fuel, you must multiply it. And if you wish to triple the velocity, the fuel mass multiplies again, not by 3, but by a far steeper multiplier still. Think of it this way. A rocket must carry not only its payload, the instruments, the supplies, the precious cargo you wish to send onward, but also the fuel to accelerate that payload. Yet the rocket must also carry fuel to accelerate the fuel itself, and then fuel to accelerate that second layer of fuel, and on, layer beneath layer, an ever-growing pyramid of material that must be lifted from the Earth before the rocket can even begin its journey outward. When we launched the Apollo spacecraft toward the Moon in the 1960s, we needed approximately 3.5 tons of rocket mass for every single kilogram of payload that actually reached lunar orbit. 3.5 to 1. The Moon is only 3 days away. 3 days of travel through the cosmic dark. Yet already the equation was demanding that we construct the largest, most powerful machines humanity had ever built. The Saturn V rocket stood as tall as a 36-story building. It consumed its weight in fuel in mere seconds. Now imagine the mathematics if you wish not to reach the Moon in 3 days, but to reach Proxima Centauri in a human lifetime. Imagine needing to sustain acceleration, or at least maintain velocity, not for 3 days, but for 30 or 40 or 80 years. The numbers cease to feel like quantities and begin to feel like abstractions, like theoretical exercises that describe something impossible. Some calculations suggest that to send even a small robotic probe to Proxima Centauri within the span of a century would require fuel masses measured in the millions of tons, or the billions. A spacecraft the size of a house would need to be surrounded by oceans of propellant just to build up the necessary speed. And that is only the beginning of the cruelty, because the faster you wish to go, the more fuel you need, but the more fuel you carry, the more mass your rocket must push against gravity. So your engines must work harder to accelerate all that fuel, which means you need even more fuel to accelerate the additional mass of your engines, which means the spiraling deepens. The equation locks you in a feedback loop of exponential growth. There is a thin mathematical elegance to it, in a way. The universe is not hostile by accident. It simply operates according to principles that are indifferent to our wishes. The rocket equation is not cruel because it wants to be. It is cruel because it is true. It describes reality, not malice. Engineers and designers have spent decades searching for ways to escape this trap. They have imagined rockets that shed mass as they climbed, leaving empty fuel tanks behind, staging their acceleration in clever sequences. And this works. Multi-stage rockets do become more efficient, because you are not carrying dead weight into the upper atmosphere and beyond. Yet even staging cannot abolish the fundamental principle. The equation always remains, waiting, patient, immovable. When we think about what it would actually take to carry people, with life support systems and food and water and radiation shielding and all the accumulated weight of their hopes and fears, across the light years to another star, the numbers become almost dreamlike in their vastness, and that is before we even account for the question of how to slow down once you arrive, how to reverse all that momentum you have accumulated over decades of hard vacuum travel. To decelerate at the end requires as much fuel as accelerating at the beginning, unless you are content to arrive at Proxima Centauri at a speed that would tear any spacecraft and any human body to atoms in an instant. The equation shows us something essential about the nature of human ambition meeting physical law. We have managed to place machines in orbit around distant planets. We have sent robots to the surface of Mars. We have flung probes beyond the edge of the solar system into the waiting dark. Each of these achievements required the equation to be negotiated and wrestled with and satisfied. But each of these distances is tiny compared to the gulf between stars. The equation does not forbid starflight. It simply demands, in exchange, a price so high that we must ask ourselves whether we are willing or able to pay it. Yet even as we understand the equation's relentless mathematics, there remains a stubborn human impulse to imagine around it, to find a loophole, to ask not whether we can break the laws of physics, but whether we might coax them into giving us just enough. In the 1950s, a group of physicists at General Dynamics looked at the nighttime sky and had an idea so audacious that it seems almost quaint now, though it was terrifying at the time. They asked, what if we could ride on the shockwave of our own atomic bombs? What if we turned the very weapons of our age into engines? This was Project Orion, and it was neither fantasy nor pure science fiction. It was engineering, cold and real, worked out on paper by serious men during the height of the Cold War. The concept was deceptively simple. A spacecraft would sit atop a long shaft, a spring mechanism absorbing the shock. And then, below that, you would detonate a nuclear device. The blast would push against a plate beneath the ship, propelling it upward. Then another explosion, then another, each one a pulse, a rhythmic hammer blow against the void, carrying the vessel faster and faster into the black. The beauty of Orion was that it actually worked, mathematically speaking. A ship designed this way could theoretically reach a significant fraction of light speed, perhaps 10 or 20%. To our present understanding, that would cut the journey to Alpha Centauri from tens of thousands of years down to mere centuries. Centuries. Can you feel the shift? It is still unimaginably long, and yet it begins to move from the realm of the impossible into something almost conceivable. But Orion had one insurmountable problem, and it was not a problem of physics, but of politics and human survival. The Outer Space Treaty of 1967 forbade the detonation of nuclear weapons in space or on celestial bodies. It was a choice born from fear. The world did not want the heavens turned into a battlefield, and it remains, in many ways, a wise one. Project Orion quietly died. The dream of riding on atomic thunder was shelved, and it has never quite returned, though every now and then a physicist will look back at those old calculations and wonder. But the impulse never truly faded. It simply took different forms. Where Orion used fission, fusion offers a gentler cousin to nuclear propulsion. Imagine not explosions, but controlled reaction, controlled fire. In a fusion engine, atomic nuclei would be fused together under tremendous pressure and heat, releasing energy far more cleanly and efficiently than fission. The exhaust would be nearly pure energy, shooting out the back of the spacecraft at unprecedented velocities. This is not just speculation. It is theoretically sound physics. In some formulations, a fusion-driven ship might reach perhaps 5 or 10% of light speed as well, perhaps more with newer designs still being sketched out on university notepads and computer screens around the world. The difficulty is that controlled fusion on Earth remains, after 70 years of effort, perpetually just out of reach. We can create fusion reactions, yes, but only at the cost of enormous energy inputs. We have not yet achieved what we call ignition, the point where a fusion reaction produces more energy than we put into starting it. And if we cannot do it on Earth, where we have all the resources and laboratories and centuries of accumulated knowledge, how could we do it in a spacecraft, far from resupply, far from repair, hurtling through an environment of extreme cold and radiation and the infinite patience of the void. Still, the theoretical advantage is tantalizing enough that serious researchers continue to work on it. There is something in the human mind that refuses to accept certain limitations, even when those limitations seem written into the fabric of reality itself. We look at fusion and think, if only we could crack this one remaining problem, if only we could light this fire and ride it outward. Some have imagined even more exotic variations, ion drives, where charged particles are accelerated through electromagnetic fields with elegance and efficiency, though at lower velocities. Proton-proton engines theoretically fueled by the very hydrogen that drifts between the stars, using it as both fuel and the medium of propulsion. Antimatter engines, where matter and antimatter are brought into contact, annihilating each other in a burst of pure energy released with almost perfect efficiency. This is not perpetual motion, not a free lunch, but it is a glimpse of what becomes possible if we could only master such reactions, if we could contain the violent dance of particles and harvest their destruction for our purposes. Yet with each advance in propulsion theory, we encounter a strange and humbling pattern. The faster we wish to go, the more ingenious our engine must be. The more ingenious our engine, the more fragile it becomes. The more fragile it becomes, the more likely it is to fail in the harsh environment of the interstellar medium. There is a kind of cosmic irony in this, a design paradox that seems almost deliberate. It is as if the universe is saying, "I will show you how this might be done, but I will make you earn every kilometer." A fusion drive represents perhaps the most realistic of the advanced propulsion concepts we might feasibly develop within the next century or so. Not tomorrow, not next year, but perhaps. And if we succeeded, if we truly managed to build and test and deploy such a drive, the journey times would shrink, not to comfort, not to simplicity, but to something that begins to edge toward the realm where human generations might actually contemplate the attempt. We would be talking about centuries instead of millennia. We would be talking about ships that might carry 10 generations, perhaps 15 instead of 100. Is that progress? Is that hope? Or is it merely a different flavor of impossibility? Perhaps both. And perhaps that is exactly the point. That we keep asking, keep imagining, keep reaching, even as the distance between the reaching and the grasping remains so vast that it seems to swallow all our ambition and leave us standing once again at the shore, looking outward into a sea we may never cross. Beyond the nuclear pulse, beyond even the theoretical fusion reactor that might one day hum at the heart of a starship, there exists a frontier of speculation so profound that it hovers between genuine physics and the territory of dreams. We are speaking now of the engines that remain purely theoretical, the ones that physicists discuss in hushed tones in university seminars, knowing that decades or perhaps centuries must pass before we might even attempt to build them. And among these, the most tantalizing, the most seductive, is the antimatter engine. For most of human history, antimatter was merely an equation on a blackboard. In the 1920s, the British physicist Paul Dirac predicted it through pure mathematics, and the universe obliged by confirming his prediction. Every particle of matter, it turned out, has an antimatter twin, identical in almost every way except for one crucial difference. Its electrical charge runs in the opposite direction. When matter and antimatter meet, they annihilate, they cease to exist, and in that instant of mutual destruction, they release energy according to Einstein's famous equation, E equals mc squared. A kilogram of matter meeting a kilogram of antimatter would produce an explosion equivalent to a thermonuclear weapon. The conversion is total, perfect, complete. This perfection is precisely what makes an antimatter engine so seductive to those who dream of crossing the void between stars. Imagine, for a moment, a spacecraft fitted with a containment chamber so sophisticated, so impossibly precise, that it can hold a few grams of antiprotons suspended in a magnetic field, hovering just barely from contact with any normal matter. Into this same chamber, normal matter is fed in controlled quantities. The annihilation happens at a measured rate, not all at once, but continuously, releasing vast streams of pure energy that is channeled through a nozzle, creating thrust. An antimatter engine, in theory, could achieve a specific impulse, a measure of efficiency, of nearly 100%. Nothing we can currently build comes close. With an antimatter engine, a spacecraft could potentially reach speeds of 10, or even 20, or perhaps even 30% the speed of light. At such velocities, the journey to Proxima Centauri, our nearest stellar neighbor, might take somewhere between 15 and 30 years. For a crewed mission, this changes everything. The travelers aboard would still age. They would still need food, water, air to breathe, but they might arrive while still young enough to explore. They might witness the arrival themselves. And yet, the practicalities are staggering, and they must be stated plainly, because antimatter remains in the realm of theory, not because of a lack of ingenuity, but because of barriers so immense that they dwarf the problems we have already discussed. Producing antimatter requires vast amounts of energy. We have created small quantities in laboratories, using particle accelerators that consume the electrical power of small cities. To fuel even a modest spacecraft with enough antimatter to reach another star would require producing and storing quantities that are, by our current understanding, practically impossible. We would need factories dedicated solely to antimatter production, running for decades, perhaps longer, and the cost would be astronomical, measured not in billions or trillions, but in resources and energy that might dwarf the economic output of entire nations. Then there is the problem of storage. Antimatter cannot touch normal matter, or both are annihilated, so it must be suspended in a magnetic field, a containment system so delicate, so prone to failure, that a single power fluctuation would result in catastrophe. A spacecraft containing antimatter is, in some sense, a flying bomb, waiting for the slightest accident to transform into an explosion of unimaginable force. For these reasons, antimatter engines remain theoretical. Brilliant, yes. Possible, perhaps. But not near, not soon. Yet there are other ideas, other whispers in the halls of physics departments and aerospace laboratories, ideas that seem equally distant but equally tantalizing. What if we could somehow bend space-time itself, creating a warp bubble that would allow a spacecraft to effectively move faster than light without actually accelerating to light speed? This is the concept behind the Alcubierre drive, a mathematical solution to Einstein's field equations proposed by physicist Miguel Alcubierre in 1994. It remains, even now, purely speculative. It would require exotic matter with negative energy density. It would demand the manipulation of space-time itself. Yet it exists as a solution to the fundamental equations that describe our universe. The laws of physics, at least as we understand them, do not forbid it. What about quantum tunneling on a macroscopic scale? What about harnessing the zero-point energy that quantum mechanics suggests permeates every cubic centimeter of space? What about harvesting the rotational energy of a black hole, using something called the Penrose process to extract power from the very fabric of space-time itself? These ideas range from speculative to purely imaginative, but they all share something in common. They represent humanity's refusal to accept the universe's constraints as final. They are the dreams of people who look at the distance between stars and ask not only how far it is, but how one might bend, shift, or sidestep that distance entirely. The honest truth is that these concepts exist not as blueprints for engineers, but as reminders of the vast territory of what remains unknown. An antimatter engine, if it could be built, would likely appear almost miraculous to someone from a century ago. And perhaps, looking back, the technologies and methods that eventually carry humanity to the stars will seem equally miraculous to us now, equally impossible, equally beyond the reach of current understanding. For now, they remain where all genuine innovation begins, in the imagination, in the mathematics, in the patient work of people willing to ask questions that have no certain answers. As a spacecraft carrying human travelers accelerated closer and closer toward light speed, something deeply strange would begin to happen, something that seems to violate every intuitive sense we have about time itself. The crews aboard would age more slowly than the people left behind on Earth. This is not metaphor or poetic exaggeration. This is the lived, measurable reality predicted by Einstein's theory of special relativity, and it has been proven countless times in laboratories around the world with atomic clocks and fast-moving particles. Imagine a ship pushing away from Earth at a speed so extraordinary that it reaches 95% the speed of light. The travelers aboard feel nothing unusual at first. They move through the cabin, eat meals, sleep in their bunks, mark the passage of days on calendars. From their perspective, time flows normally, the way it always has. 1 year passes, then 5, then 10. The ship's chronometers tick forward steadily. The crew members grow older, but only slightly. A person who was 30 years old when departure might be only 38 or 39 by the time a decade has elapsed aboard the vessel. But on Earth, the situation unfolds very differently. Decades accumulate. 30 years pass. 40, 50. Children born on the day of departure are now older adults. Buildings have been constructed and demolished. Political systems have risen and fallen. Entire generations have lived their complete lifespans while the spacecraft hurtles through the void. When the ship finally arrives at its destination, perhaps Proxima Centauri, the nearest star beyond our Sun, lying 4.24 light-years away, the travelers aboard might have experienced only 15 or 16 years of subjective time, but on Earth, more than 70 years will have elapsed. This is the strange gift and burden of relativity. The faster an object moves through space, the more slowly it moves through time, relative to observers at rest. This is not a quirk of clocks or a misunderstanding of how we measure moments. It is woven into the fabric of reality itself. The speed of light is constant for all observers, everywhere in the universe. To maintain this constancy, something else must give. That something is time itself. The equations are elegant and precise. The time dilation factor grows smaller as velocity increases. At 10% light speed, the effect is almost negligible. A journey that takes a century for Earth observers might take 98 years for travelers. But as the spacecraft accelerates beyond 50 or 60% light speed, the effect becomes more pronounced. By the time a ship reaches 95% light speed, time aboard moves at roughly 1/3 the rate of time on Earth. Decades can compress into years. There is a profound loneliness in this asymmetry, is there not? The travelers depart with a goal, with a sense of mission, with perhaps the hope of returning someday to tell the tale of what lies beyond. But everyone they knew, everyone they loved, will be dust long before they reach their destination. A woman who leaves Earth might spend 15 years in transit and arrive at a neighboring star system to find that everyone she knew, all her family, all her friends, have lived their lives, aged, and died. Her journey, measured in the subjective experience of her body and mind, is brief, but measured against the history of Earth, it spans generations. Some have proposed that this creates a paradox of motivation. Why volunteer for such a mission, knowing that your sacrifice will not be recognized for centuries? Why endure years of confinement and danger to reach a star when you will find no one left at home who remembers your name? Yet perhaps there is nobility in this very surrender, to be willing to venture into the darkness not for reward, not for recognition, but simply because something in the human spirit yearns to know what lies beyond. The effect could also work in the traveler's favor, in a curious way. A mission to Alpha Centauri that would take over 400 years measured in Earth time might be completed in less than 100 years measured aboard the spacecraft. The subjective experience of those aboard would be far shorter, far more survivable. Time itself becomes a kind of propulsion system, a gift of physics that makes the impossible slightly less impossible. A human lifetime, stretched and compressed by the curvature of space-time, might just suffice to reach the stars. But there is a catch, of course, and it is one that brings us back to the energy question that seemed so daunting before. To achieve speeds high enough that time dilation becomes truly beneficial, perhaps 85 or 90% light speed, a spacecraft would need to accelerate to those velocities, and the amount of energy required grows not merely linearly with speed, but exponentially. The relativistic kinetic energy of an object climbing toward light speed becomes astronomical, literally incomprehensible. The very laws of physics that give us this gift of time compression also demand a price so steep that paying it seems almost beyond the reach of any civilization constrained by mere matter and mere energy. And yet, somewhere in this paradox lies a strange possibility. Perhaps time itself is the answer. Perhaps a civilization far more advanced than ours, a species that has mastered not just nuclear fusion, but matter-energy conversion, could afford to pay that price. Perhaps some distant future humanity, or some post-human successor, could harness the power of stars themselves to push a vessel to such speeds that the travelers aboard would experience mere years, while centuries unfolded behind them. They would arrive at another world not as relics of a forgotten age, but as representatives of a future that, to them, feels like it has barely begun. The mystery of time dilation reminds us that the universe does not forbid interstellar travel through any law we have discovered. It merely makes it strange, difficult, lonely, and profoundly asymmetrical. And in that asymmetry, there is something almost beautiful, a reminder that the cosmos is far stranger than our everyday intuitions can grasp. And so we arrive at perhaps the most profound puzzle of interstellar travel, one that shifts the question from engineering to something far more intimate and unsettling. What if we built a ship so massive, so resilient, that it could carry not just fuel and instruments, but entire families, generations upon generations, sailing across the void toward a destination no living person aboard will ever see? The generation ship is an idea as old as our awareness of cosmic distance itself. In the 1970s, scientists and philosophers began to ask seriously, could we construct a vessel large enough to sustain a self-contained civilization for centuries? A world unto itself, spinning slowly to create artificial gravity through centrifugal force, with hydroponics gardens stretching along its interior, water recycling endlessly, air scrubbers humming in the darkness. The engineering, while staggering, seemed almost achievable compared to the physics of relativistic travel. But the moment you truly contemplate it, the moment you imagine those families boarding such a vessel knowing their grandchildren's grandchildren will die still traveling, something shifts. The practical questions become moral ones. The technical problems become questions about meaning itself. Consider first the sheer biological task. A generation ship carrying perhaps 10,000 people, the minimum estimated for genetic diversity and avoiding debilitating inbreeding over centuries, would need to manage reproduction with extraordinary care. You cannot simply let people pair and multiply as they wish. The ship's resources are finite. Every child born is a mouth that must be fed from carefully rationed nutrients, air that must be scrubbed by machines, water that must be recycled. And yet you cannot restrict reproduction too severely, or you risk psychological collapse. What keeps a civilization bound together when every person born knows with certainty they will die in transit, that their children will die in transit, perhaps their great-grandchildren too? The question becomes almost unbearable when you truly sit with it. How do you explain to a child born in the hollow belly of a spacecraft that everything they see, the curved walls, the artificial sun, the recycled water, is not the natural world at all, but a cage? That they are part of a sacred trust, a relay race in which they run toward a finish line they themselves will never cross? Some theorists have proposed managing this through careful social engineering, through education that frames the journey as a profound honor rather than a burden. Children aboard a generation ship might be raised with a kind of cosmic spirituality, taught from their earliest moments that their lives have meaning, precisely because they are part of this grand crossing, that they are threads in a tapestry stretching across centuries. There is something almost religious about such an approach, and one cannot help but wonder whether future generations might eventually reject this framing. What if the children born in the 7th generation begin to ask why they should accept this burden? What if they decide, as humans so often do, to rebel against the purposes their ancestors set for them? There is also the question of knowledge and decision-making. A generation ship would need governance structures that could hold for centuries. How do you prevent tyranny when communication with Earth has become impossible, when the ship's leaders have absolute control over all resources and all information? How do you ensure that the mission itself, the journey to another star, remains worth pursuing, especially if faster methods of travel are later invented by people still on Earth? What moral obligation do the later generations have to a destination chosen by ancestors they have never met? And then there are the biological challenges beyond mere reproduction. Humans evolved under Earth's gravity, under direct sunlight, moving freely across vast landscapes. A ship, no matter how ingeniously designed, cannot perfectly replicate such an environment. The artificial gravity created by rotation can induce nausea and disorientation. The indoor agriculture necessary to produce food operates under artificial lights that, while they may provide all necessary wavelengths, carry none of the subtle variations that accompany natural sunlight. Over generations, would the human body adapt to these conditions? Would the children born and raised aboard the ship develop different musculature, different bone density, different sensitivities to light and gravity? Would they, after centuries, become as different from their Earth ancestors as we are from those who first walked upright on the savannah? There exists a curious proposal in the scientific literature called the cultural mutation problem. As each new generation is born, they inherit the knowledge of the mission through teaching and tradition, but they do not inherit the emotional and cultural commitment that drove their ancestors to board the ship in the first place. The purpose gradually becomes abstract. A child raised aboard the ship, surrounded by recycled air and artificial light, may begin to wonder why the mythical destination, Alpha Centauri perhaps, or Tau Ceti, matters more than the home they have known since birth, the only home they have ever truly known. The gravity of Earth becomes less real to them than the manufactured gravity of the ship's rotation. Some researchers have suggested that virtual reality might help solve this. Immersive simulations of Earth could be maintained for passengers, allowing them to feel they are walking on soil, feeling natural rain, gazing at an open sky. But this raises its own questions. Is comforting people with elaborate illusions a kindness or a cruelty? And what happens when someone born aboard the ship experiences such a simulation and then asks, with genuine confusion, why they should ever leave such paradise to board a vessel and travel to an uncertain destination. The technical literature explores scenarios where mutation and adaptation are acknowledged as inevitable. Perhaps the beings who arrive at the destination star system are not quite human as we understand the term now. They would be our children, yes, but changed by centuries of selection pressure in a closed environment, by genetic drift in a small population, by the subtle pressures of living in artificial conditions. Some have speculated, with a kind of gentle melancholy, that it might take not one generation ship but many, a fleet of vessels traveling at different velocities, different trajectories, so that if some vessel's civilization collapses or diverts from the mission, others might still complete the journey. And there is one more puzzle, perhaps the quietest and most haunting, the question of memory. The ship carries libraries, archives, digital storage of all human knowledge and history, but does it carry, somehow, the memory of Earth itself? Each generation born aboard knows Earth only through recording and teaching. For the 10th generation, for the 15th, Earth is not a place they have ever been. It becomes mythology, a sacred origin story, no different in its psychological weight than the mythical Avalon or Olympus. What happens to a civilization when its origin point becomes indistinguishable from legend? But there exists something far more insidious than the vastness itself, something that travels alongside every star in the galaxy and waits between them in a patient, diffuse silence. The interstellar medium, that vast ocean of gas and dust floating between the suns, harbors dangers that no amount of fuel or clever engineering can wholly dispel. To travel between stars is not merely to cross an empty void, as we might once have imagined it. It is to navigate a realm thick with hazards so subtle, so pervasive, and often so poorly understood that they constitute perhaps the cruelest test of our ambitions to leave home. Imagine, if you will, stepping outside on a clear night and looking up at the stars. The space between them appears, to our eyes, to be nothing, complete darkness, absolute emptiness. Yet this perception is a profound illusion born from distance. The truth is far more complex and, in many ways, far more troubling for anyone who dreams of crossing that gulf. The universe is not empty. It is filled with a thin, almost unimaginably dispersed cloud of hydrogen gas, helium, and trace elements, the remnants of ancient supernovae, the exhalations of dying stars, the slow decay of stellar nurseries that gave birth to suns billions of years ago. This interstellar gas exists in concentrations so low that we would consider it a perfect vacuum by terrestrial standards. And yet, across the vast distances between stars, these sparse atoms accumulate. Across light years, the sparse becomes significant. Across the distances our fastest spacecraft would need to travel, significance becomes danger. When a vessel attempts to cross the interstellar medium at velocities approaching even a fraction of light speed, and any journey to the nearest star would demand such velocities, each encounter with an atom or dust particle becomes a collision. Think of it not as moving through empty space, but as ploughing through an invisible ocean at unimaginable speed. At relativistic velocities, an atomic collision generates energy equivalent to a nuclear reaction. A single hydrogen atom, encountered at near light speed, releases energy comparable to that of a substantial explosion, and a spacecraft traveling the light years to another star would encounter not one atom, but trillions upon trillions of them. The phenomenon is known, soberly, as ablation erosion. The outer hull of any vessel would be slowly vaporized by this constant, imperceptible bombardment. The impact flux, the sheer number of particles striking the spacecraft per unit time, would gradually eat away at every exposed surface. Engineers have proposed various defenses. Some suggest hulls of exotic materials, layered with shielding designed to absorb repeated atomic impacts. Others propose magnetic fields of tremendous strength, arranged to deflect charged particles away from the vessel's body. Yet each solution introduces new burdens of mass, new demands on power systems, new complexities to a journey already stretching the limits of what we can conceive. And the dust is far worse than the gas. Dust particles, though rarer than free atoms, carry far greater mass and energy. A grain of dust the size of a salt crystal, encountering a spacecraft at a significant fraction of light speed, would impact with the force of a bullet. At near-light velocities, such a collision would be catastrophic. A kilometer-sized cloud of such particles would be deadly. And our interstellar neighborhood, it seems, is not free of such clouds. Dense dust lanes and nebulae are found throughout the galaxy. Some are visible to us from Earth, dark patches in the sky where dust obscures the light of distant stars. Others exist in regions we cannot yet see, but must prepare to encounter. Cosmic rays present an even more pervasive hazard, one that cannot be fully shielded against without adding prohibitive mass. These high-energy particles, protons and heavier atomic nuclei, energized by distant supernovae and the tumultuous cores of galaxies, stream constantly through space in all directions. A spacecraft and its occupants would be exposed to a steady, relentless background of radiation far exceeding the cosmic ray exposure experienced by astronauts in Earth orbit. Over months and years of interstellar travel, the cumulative dose would become severe. Shielding from cosmic rays requires either massive, heavy layers of material or active magnetic fields consuming enormous power. For a vessel that must already carry enough fuel to approach light speed, the additional burden of radiation protection becomes yet another cruel compromise. There is something quietly poignant in this realization, isn't there? We have engineered our way around gravity with rockets. We have learned to master the vacuum itself through pressure suits and sealed compartments. And yet the invisible, diffuse hazards of the interstellar medium remind us that some obstacles cannot be overcome simply through ingenuity. Some challenges persist, not because we lack imagination, but because physics itself imposes limits. The radiation damage to electronic systems poses its own distinct problem. The microchips and sensors that would guide an interstellar vessel rely on the precise arrangement of electrons within silicon lattices. Cosmic rays and other high-energy particles can disrupt these arrangements, causing what engineers call single-event upsets, moments when a stray particle corrupts data or causes a temporary malfunction. In a spacecraft far from Earth, with no possibility of rapid repair, such upsets accumulate. Radiation-hardened electronics exist, designed specifically to withstand cosmic rays, but they are more expensive, often less capable, and still not immune to the constant assault. And then there is the question of unknown hazards, the threats we cannot yet predict because our surveys of the interstellar medium remain incomplete. What rogue asteroids might drift between the stars, invisible until the moment of impact? What magnetic anomalies or regions of unexpectedly dense plasma might lie in wait? The history of exploration is filled with the discovery of unexpected dangers. We might engineer flawlessly for the hazards we know and still fall victim to ones we have not yet imagined. Some scientists have proposed that these barriers, the radiation, the dust, the subtle erosion of the void, may prove insurmountable, not absolutely, but practically. That is, they might not make interstellar travel theoretically impossible, but they make it so expensive, so demanding, so technically challenging that the effort becomes unreasonable. They represent a creeping accumulation of obstacles, each manageable in isolation, but collectively forming a wall of difficulty that grows higher the more precisely we examine it. Yet even in contemplating these hazards, there is something oddly humbling and beautiful. The interstellar medium, for all its dangers, is not hostile in intent. It is simply itself, the natural state of the universe, indifferent to our ambitions, neither welcoming nor rejecting our efforts. To cross it would be to persist despite these challenges, not to overcome some malevolent force, but to navigate patiently through the ordinary hazards of an ancient cosmos. The dust and radiation and diffuse gas are not enemies. They are simply the price of admission to the realm between the stars. And so we arrive at a dream as old as the dream of stars themselves. If the distances are truly too great for our waking bodies to cross, what if we could simply sleep through them? What if a crew could drift into profound unconsciousness at the edge of Earth's orbit, their hearts barely beating, their minds suspended in the vast dark, and wake only when the journey's end appears on the horizon? It is perhaps the most seductive of all interstellar fantasies, because it promises escape from the cruelest part of space travel, not the speed, not the fuel, but the terrible patience required, the waiting, the watching of years dissolve into decades. Cryogenic sleep, or suspended animation as it is sometimes called, holds a particular place in our collective imagination. Science fiction has long presented it as almost solved, a mere technical detail waiting for the engineers to perfect. We have read of crews frozen in their chambers, ice crystalline against their skin, traveling through the dark without aging, without hunger, without the slow psychological dissolution that comes from years confined in a metal tube. It is deeply appealing precisely because it seems to solve so many problems at once. Time dilation, after all, requires velocities that strain every known physics and demand fuel we cannot imagine. But suspended animation requires only that we understand the human body well enough to slow it nearly to stillness, and then reverse the process. How difficult could that be? The difficulty, as it happens, is almost everything. The human body is not a machine that can simply be paused. It is a symphony of chemical reactions, electrical impulses, cellular processes so intricate that we are still discovering new layers of complexity. When we cool the body, we do slow metabolism. This is not speculation. It is observed fact. Hibernating animals reduce their metabolic rate dramatically during winter, and some creatures can survive being partially frozen. Cold water drowning victims have survived extended periods with minimal brain activity, their bodies preserved in what is sometimes called a state of apparent death. The principle exists in nature, quieter and slower, and far more profound than the gentle sleep of fiction. But there is a distance between slowing and stopping, and that distance is where the real troubles begin. As temperature drops, cells become fragile in ways that are only now becoming fully understood. Ice crystals form within and between cells, and these crystals do not form slowly or gently. They shatter cell membranes. They rupture the delicate structures within, the mitochondria, the nucleus, the intricate machinery that keeps a cell alive. Even if we cool the body slowly, even if we use cryoprotectants, chemicals that prevent ice formation and replace water in the spaces between cells, we are still asking the body to endure a profound insult. The longer the suspension lasts, the more damage accumulates. Proteins begin to denature. Metabolic byproducts accumulate in tissues. The central nervous system, that most precious and irreplaceable of human structures, is particularly vulnerable to cryogenic injury. No animal has ever been cryogenically frozen and successfully revived intact. Not a single one. We have frozen and thawed small tissues, individual organs in laboratory conditions, maintaining cell viability for hours or sometimes days. But a whole organism, a human brain, the technology does not exist, and the obstacles are not merely technical, they are fundamental to how biological systems work. A being is not merely the sum of its cells, it is the precise arrangement of those cells, the intricate web of neural connections that comprise consciousness, the delicate balance of every subsystem working in concert. Disrupt that architecture at the cellular level, and when you reassemble the pieces, are you reassembling the person, or something else entirely? There are researchers working at the edges of this frontier, pushing toward what they call vitrification, the idea that instead of freezing, we might transform the body into a glass-like state, bypassing the ice crystal problem altogether. It is theoretically elegant. It has been successfully demonstrated in small tissue samples. There are those who believe that in decades, perhaps a century or more, we might perfect the technique for larger and more complex organisms. Some people have already arranged to be vitrified after death, preserving their bodies in liquid nitrogen, in the hope that future generations will possess both the technology and the desire to revive them. It is a bet against death itself, a kind of faith extended across time. But even if we solve the freezing problem, even if we perfect vitrification and learn to revive a human being intact after months or years in suspension, we have only solved part of the puzzle. What of the psychological cost? A person awakens from cryogenic sleep to find that decades have passed. Everyone they knew has aged or died. The world has transformed. The technology that revived them has become mundane, already being superseded by newer innovations. They have lost their entire society, their era, their context. They have become a ghost in their own future. And this is not a small thing. The human mind requires continuity, meaning, connection. Is survival in isolation truly survival at all? There is also the matter of the journey itself. If we place a crew in suspended animation for a voyage that might take 200 years, what happens to the ship? Machines decay. Even the most robust systems accumulate errors over centuries. Who maintains the ship? Who watches the sleeping crew, tending to the 1,000 small catastrophes that can arise? Do we need an awake crew to oversee the process? And if so, cryosleep has not solved our problem at all. We have merely pushed the burden onto those who remain conscious, standing watch across generations that they will never meet, maintaining a vessel for a journey they will never complete. The rockets we might build to reach another star could carry frozen crews, yes. The equations would not change fundamentally, but the dream of sleeping through the journey, of waking on a new world as though stepping out of a single night's rest, that dream belongs to fiction. In reality, if we ever send human beings to another star, they will almost certainly make the journey conscious. They will live and work and age. They will see the slow turning of the years. They will die and be buried in space, perhaps, their remains pressed into the void, or they will live long enough to see arrival, to plant their feet on alien soil in their final years. The journey will be lived, minute by minute, breath by breath. There is no escape from time itself, even with all the technology we might eventually develop. And yet the dream persists, does it not? The dream of closure, of rest, of the possibility that we might cheat the distance by simply stepping outside of time. It speaks to something deep within us, a desire not just for the stars, but for stillness, for reprieve, for the luxury of not having to wait consciously through the long, lonely dark. Yet beneath all these theoretical frameworks, all these elegant equations and their humbling calculations, something remarkable is happening right now. In laboratories and observatories scattered across the world, a handful of visionaries are not waiting for fusion drives or antimatter breakthroughs, or the distant maturation of technologies centuries away. They are building something far smaller, far stranger, and perhaps far more plausible than anything we have yet imagined. They are building starships the size of postage stamps. Breakthrough Starshot began in the mind of Yuri Milner, a physicist and entrepreneur, who asked a deceptively simple question: what if we did not need to send a massive vessel to another star, but something impossibly tiny instead? The premise rests on a principle as old as light itself. If you could catch a photon and ride it, If you could somehow harness the pressure of light itself, could you not sail between worlds as ancient sailors once sailed between continents? The answer, surprisingly, is yes. Light carries momentum. When photons strike a surface, they push. The force is minuscule on ordinary scales, but concentrate enough light on something small enough, and acceleration becomes not merely possible, but extraordinary. Picture, if you can, a craft no larger than a grain of rice. An integrated circuit, a camera, a radio transmitter, all compressed onto a single microchip. Attached to this impossibly small computer would be an equally gossamer sail, perhaps 4 meters across, but so thin it would be nearly invisible to the human eye. Composed of materials engineered to reflect laser light with near-perfect efficiency. The entire apparatus, sail and spacecraft combined, would weigh only a few grams. Think of it as a technological whisper cast into the void. Now imagine focusing a laser beam upon it. Not an ordinary laser, but an array of them, a grid of lasers arranged on Earth, covering perhaps 100 square kilometers, each one powerful enough to light a city, all aimed at the same infinitesimal target. What would happen is almost dreamlike in its elegance. The photons would strike the sail. The sail would push back against those photons through the quantum mechanics of reflection, and in that exchange, the craft would accelerate, and accelerate, and accelerate. Within minutes, the nanocraft would reach speeds of 20% the velocity of light. Within a few more minutes, it would have traveled further than any human crewed spacecraft has ever ventured. It would be hurtling toward Alpha Centauri at a fifth of light speed, which is to say, fast enough to cross the entire solar system in a matter of days, fast enough to reach another star not in millennia, not in centuries, but in perhaps 20 or 30 years. This is not science fiction whispered in dimly lit auditoriums. This is engineering being actively developed and refined by scientists at the University of Physics in Switzerland, by researchers at Stanford, by teams working within the Breakthrough Initiative itself. The physics works, the mathematics checks, the primary obstacles are not theoretical but practical, and that distinction is profound. We know how to build lasers powerful enough. We know how to construct sails sufficiently reflective. We know how to miniaturize electronics. The challenge is to integrate these elements with sufficient precision and power, to focus the laser without the Earth's atmosphere scattering the beam into uselessness, and to somehow communicate with a grain of rice-sized transmitter as it streaks toward a distant star. These are immense engineering challenges, not fundamental impossibilities. There is something almost poetic about the audacity of it. For all our dreams of generation ships and relativistic starships, and the vast apparatus of futuristic propulsion, our most realistic path to another star may be the simplest and most elegant one, not to push against the vacuum with exotic physics, but to ride the oldest force in the universe, light itself, unchanged since the moment the cosmos began. Light, which has been traveling to us from distant stars for billions of years, now repurposed as a highway, a vehicle, a bridge across the darkness. Yet this technology carries its own profound loneliness. The craft would be autonomous, utterly alone, in a way that even crewed vessels would not be. There would be no human consciousness aboard, no witnessing presence at the moment of arrival. The nanocraft would arrive at Alpha Centauri and conduct its observations, capture its images, take its measurements, and send back what it found across the light years in radio signals that would take 4 more years to return to Earth. By then, every human who launched the mission would be old or gone. The people who received the data would be descendants, strangers in a different century. Still, there is something quietly revolutionary about the simplicity of it. We do not need to revolutionize physics. We do not need to engineer a way around relativity or discover new forces hidden in the fabric of space-time. We merely need patience, precision, and the will to cast these tiny seeds into the cosmic wind. Multiple craft could be launched in a stream, a fleet of postage stamp-sized explorers, some bound for Alpha Centauri, others perhaps for Proxima Centauri, still others for more distant targets. Each one would be replaceable, inexpensive by the standards of space exploration, and capable of surviving the journey in ways that larger, more elaborate vessels might not. The radiation of the interstellar void would still threaten them. The dust that drifts between the stars would still pose a danger, particles hitting at relativistic speeds with the force of bullets. A single grain of sand striking a nanocraft at 20% light speed would deposit the energy of an explosion. Protection would be minimal, perhaps a thin shield, perhaps merely the redundancy of multiple transmitters and sensors, so that even if most are destroyed, some data returns home. It is a grim calculus, but a realistic one. What makes Breakthrough Starshot so compelling? Perhaps the reason it has captured the imagination of so many thinking people in our moment is that it does not require us to wait. It does not demand technologies that exist only in our hopes and extrapolations. It asks us to extend our current capabilities, to push them to their limits, but not beyond them. Within perhaps 15 or 20 years, this project could launch. Within 35 to 50 years, assuming the laser arrays are built and maintained with perfect consistency, assuming the engineering challenges are solved, we could receive our first data from another star system. A child born today could grow into adulthood and see the moment when humanity's first contact with an alien star becomes reality. Not a crewed mission, not a generation ship, not even a probe in the traditional sense, but something new, a way of thinking about travel that bridges the ancient with the cutting edge, that uses the universe's most basic physics to overcome its most daunting distances. And yet even this extraordinary possibility, this laser-driven frontier, brings us to a threshold of another sort. For if we do send these nanocraft, if they do reach another star, what then? How do we hear from them across the gulf of space and time? How do we maintain connection with an instrument that has left our solar system and will never return? These questions lead us into a different realm of human challenge, one that is not about engineering or energy or physics at all, but about patience, communication, and the strange weight of isolation across cosmic distances. And yet, imagine for a moment that we have solved the propulsion puzzle. Imagine that humanity has found a way to break free of Earth's gravity well and set course toward Proxima Centauri, or one of the other nearby stars that shimmer in our night sky. The ship is built, the crew has been selected, the months of acceleration give way to the long, patient coast through the interstellar dark. They are, at last, underway. But something happens in that moment of departure that most dreamers of starflight do not fully reckon with. The communication that bound them to home begins to fray, not because of mechanical failure or solar interference, but because of something far more fundamental. Light itself, that fastest thing we know, suddenly becomes slow. Consider the mathematics of this quiet tragedy. A message sent from a spacecraft traveling toward Proxima Centauri, just 4.24 light-years away, must travel across an expanding gulf. If the ship were moving at a tenth of light speed, a realistic ambition for our distant descendants, that message home would take more than 40 years simply to arrive. Not 40 years to be read and understood, 40 years just for the signal to cross the darkness and reach the receiving stations of Earth. And then there is silence, the wait for a reply, for loved ones to read the transmission, perhaps in a language their great-grandchildren speak differently than the crew remembers, for committees to be convened, decisions to be made, words to be carefully composed, for that return message to be encoded and sent back across the void. Another 40 years of travel. So a question asked in the early stages of an interstellar voyage, a simple inquiry about resources or a cry for guidance, might not receive an answer until the crew asking it has aged 80 years. 80 years. Long enough for children born during the voyage to grow old themselves. Long enough for the questioner, if they survived cryosleep or biological modification to extend their lifespan, to have forgotten why they asked. This is not hyperbole. This is mathematics. This is the geometry of the cosmos pressing down upon human connection. The isolation it creates is almost unimaginable. Modern astronauts aboard the International Space Station can speak in real time with mission control in Houston. A delay of mere fractions of a second troubles them, an echo they must learn to work around. Even the Mars rovers, which take anywhere from 3 to 20 minutes for a signal to travel one way, operate with carefully planned contingencies because that delay is considered profound. A rover's operators cannot simply tell it to stop if it encounters danger. They must predict what it will encounter, program its responses in advance, and hope their foresight was sound. Now multiply that delay by 1,000, by 10,000. What emerges is not a conversation, but a soliloquy. The crew of an interstellar vessel would need to become entirely self-sufficient, not just in the practical sense of food and water and oxygen, but in the psychological sense. They would be, for all meaningful purposes, orphaned from home, not exiled, not rejected, simply separated by a distance that makes real-time dialogue impossible. The crews themselves would understand this, presumably. They would volunteer for it, knowing what awaited. But understanding intellectually and experiencing emotionally are different territories of the human heart. Letters might be recorded and sent home, messages in bottles cast into an ocean of starlight, and replies would come, yes, but they would arrive freighted with a strange temporal weight. The Earth they describe would be decades or centuries old by the time the crew receives word of it. Would they recognize it? Would they want to? There is a peculiar loneliness in sending a message into space, knowing that your children, if you have frozen them in cryosuspension, might not be alive to hear the answer, knowing that your grandchildren will read words from a home that no longer exists in the form you knew it. News from a dead world, a world that changed in your absence in ways you can only imagine, cannot influence, cannot comfort yourself by being part of. And then there is the question of communication failure itself. What if, during those 40 or 80 years of waiting for a response, there is a catastrophe on Earth? What if climate shifts in ways that render the old communication infrastructure obsolete? What if societies collapse and rebuild in new forms that have no interest in the slow, patient dialogue with an ancient spacecraft? The crew would never know. They would continue their voyage under the assumption that Earth was still there, still listening, still part of the shared human project. But Earth, from their perspective, would simply go silent. Some theorists have speculated about solutions, autonomous spacecraft that do not require constant guidance, artificial intelligences that can make decisions and solve problems without referring to distant human authorities, or perhaps artificial intelligences that are the travelers, digital minds that can be copied and backed up and do not suffer the isolation in the same way flesh does. These are possibilities we will explore more fully as this journey continues. But for now, in this moment of meditation on the reality of reaching beyond our world, it is worth sitting with the silence. Worth understanding that any human who travels to another star would be undertaking not just a physical journey, but a spiritual severing. They would be saying goodbye in a way that no astronaut orbiting Earth has ever had to do. They would be becoming, in some essential sense, a new species, separated from their origins not by evolution, but by the immutable laws of physics and the vast patience required to traverse the cosmos. The stars pull at us with their ancient light, but the price of answering that pull is loneliness on a scale few humans have truly contemplated. And it is this loneliness, perhaps, more than the engineering challenges or the fuel calculations that will ultimately keep us bound to our small blue world. And yet, in the quiet hours before dawn, there arrives a question that sits beneath all the mathematics and the physics and the engineering schematics we have laid out so carefully. A question so fundamental that it may reveal more about who we are than any rocket equation ever could. Why do we yearn for the stars at all, knowing as we do, truly knowing now, in the depths of this understanding, that the very fabric of space and time has been arranged in ways that may make the journey impossible? There is something in the human mind that seems built to reach beyond the horizon, even when reason whispers that the horizon recedes faster than we can ever travel. Our ancestors looked up from the African savanna and wondered what lay beyond the ridgeline. They built boats and crossed oceans that seemed infinite. They climbed mountains that their grandparents said would kill them. And when every reachable place on Earth had finally been reached, what did we do? We turned our eyes upward, toward the void, and asked the same ancient question: what is on the other side? Perhaps this longing is not really about the destination at all. Perhaps it is about the reaching itself, the assertion that we are creatures capable of growth, of movement, of transcendence. To dream of the stars is to say, in some profound way, that we refuse to accept limitations, even the limitations written into the very laws of the universe. There is a kind of defiant beauty in that refusal. Consider what it would mean to send a generation ship into the darkness, knowing that you will not live to see its arrival, that your children will not live to see it, and that your great-great-grandchildren may not see it either. You are choosing to work toward a goal that your own eyes will never witness, for a future you will not inhabit, for a promise you are making to people not yet born. What does it say about humanity that we are capable of such patience, such faith, such willingness to labor on behalf of centuries we will never know? It is not the patience of animals, who live only for the immediate moment. It is not even the patience of civilizations, which think in generations and centuries. It is something stranger and more beautiful. It is the patience of dreamers, beings capable of holding in their minds an image of a future so distant that it exists almost in the realm of myth, and choosing to work toward it anyway. The stars become less a destination and more a meaning maker. They become proof that we are something more than the sum of our brief days on one small world. And what of the loneliness implicit in this dream? A spacecraft hurtling through the void for decades or centuries, growing farther from Earth with every passing year, until radio signals take so long to travel that conversation becomes almost impossible. The crew, or their descendants, would be utterly alone in a way that no human in history has ever truly been alone. They would be beyond rescue, beyond help, beyond the reach of any other human presence. The isolation would be absolute. Yet there is something in the human spirit that seems to find meaning, even in, perhaps especially in, solitude. We have always been drawn to the idea of the explorer, the adventurer who ventures into the unknown and accepts the loneliness as the price of discovery. The generation ship becomes an extreme version of this archetype. The people aboard would be heroes, not because they accomplish something immediately spectacular, but because they endure, they persist, they continue forward through years of darkness toward a light they may never see. This raises a subtle and rarely spoken truth. Perhaps the real barrier to interstellar travel is not physics or engineering, but something far more intimate. It is a question of human will and human nature. Are we patient enough? Are we brave enough? Are we willing to sacrifice immediate comfort and safety for a goal that belongs to our descendants? History suggests we struggle with these questions. We live in an age of accelerating desires, of immediate gratification, of quarterly reports and election cycles. We have become a species that prefers small gains today to vast gains tomorrow. The dream of reaching the stars, then, becomes less a prediction about our future and more a mirror held up to our present. When we talk about why we might never reach another star, we are really asking questions about ourselves. Do we have the patience? Do we have the unity of purpose? Do we have the willingness to think beyond our own lifespans? Do we value the journey, even when the destination recedes into the impossible distance? There are moments in human history when we have answered these questions with a resounding yes. We have built cathedrals that took centuries to complete, knowing we would not see their completion. We have created art and music and literature for audiences centuries away. We have planted trees whose shade we would never sit beneath. We have worked towards social changes that we knew would only fully flower after our deaths. In these moments, we touch something eternal in ourselves, something that reaches beyond the prison of our own mortality. The stars, perhaps, represent the ultimate expression of this impulse. They ask of us the hardest work of all, to dream of something so distant, so difficult, so seemingly impossible, that it requires not just our effort, but the effort of thousands of people working together over generations, united by a vision they may never see realized. The very act of reaching toward the stars, even if we ultimately fail, even if the laws of physics make it impossible, that act itself becomes a statement about what we are and what we aspire to be. And in that way, the journey toward the stars is never truly doomed, because even if the destination remains forever beyond our grasp, even if the void proves impassable, even if we discover that the universe has locked us on this one small world for all of time, the reaching itself is the point. The yearning itself is the answer. We are the kind of creatures who dream of the impossible, and perhaps that is what makes us human. Perhaps, though, the question that has begun to shift in the minds of some scientists and engineers is not whether we ourselves must be the ones to go, but whether we must go at all. It is a strange inversion of the dreams that came before, not the heroic human explorer stepping foot on a distant world, but rather the quiet machine, tireless and patient, carrying our knowledge and our curiosity across the centuries while we remain in the safety of our home. And there is a curious comfort in this thought, is there not? A way of reaching the stars that asks nothing of flesh or bone, that demands no generation of unborn children sacrifice their lives to a journey they did not choose. The robotic probe has long been the workhorse of human exploration, silent witnesses to the inner solar system's wonders. Voyager and its twin, launched in the 1970s, still carry golden records spinning through the darkness, still send their whispered signals back across the vast gulf they have traveled. But those journeys were merely steps across our cosmic doorstep. The distances to nearby stars demand something altogether different. A spacecraft built to survive the radiation and micrometeorite impacts of interstellar space, hardened against the slow degradation that time itself seems to inflict on all things. Such a vessel would need redundancies upon redundancies, the capacity to repair itself when no human hands could possibly reach it, no spare parts could possibly arrive in time. And yet, this is becoming less a problem of engineering and more a problem we have already begun to solve. What if such a probe carried not merely instruments and cameras, but something closer to a mind? Artificial intelligence, in its current forms, still fumbles like a child learning to speak. The systems we have created are narrow in their talents, brilliant within their particular lanes, but incapable of the kind of flexible, general reasoning that a human explorer brings to an unknown world. And yet they improve with a speed that bewilders even those who work closest with them. Imagine, if you will, a probe dispatched to Proxima Centauri, carrying within it an intelligence vast enough to understand science, to make decisions, to troubleshoot problems no one on Earth could have foreseen. Such a mind would not grow bored across the 40 years of travel it might require to reach its destination. It would not yearn for home in the way a human astronaut would. would not grieve the loss of a life lived in isolation. When it arrived, it could explore and experiment and learn, sending back to us the fruits of its discoveries. It would be, in a very real sense, our eyes and hands on another world, without the terrible cost of putting human beings on a path of no return. But there is something that troubles many when they contemplate this future, and it is worth sitting with for a moment. If such an intelligence existed, would it truly be our emissary at all? Or would it be something far more alien to us than even the most distant star? We talk about consciousness in hushed, uncertain tones, for it remains one of the great mysteries, and the question of whether a machine could possess it, or whether such a question even makes sense, remains stubbornly open. Would an artificial intelligence experience its journey through the void? Would it find meaning in what it discovered? Or would it be, in essence, a very sophisticated calculator, performing its functions with perfect efficiency while possessed of nothing resembling wonder or understanding? The answer, if we are honest, remains uncertain, and perhaps uncertainty is itself part of the appeal. Then there emerges an even stranger possibility, whispered about in certain academic corridors and speculative conferences, the idea of digital consciousness itself, untethered from any physical substrate. What if we did not send a machine that was trying to be intelligent in the way humans define intelligence, but rather a copy of a human mind? The technological challenges here are staggering, perhaps insurmountable with our current understanding. We would need to fully understand the brain, not merely its structure, but the precise electrochemical patterns that give rise to consciousness itself. We would need to map it at a resolution that seems to demand technology we do not yet possess. And having done so, we would need to upload that pattern to a computer system, to create a duplicate mind running on silicon rather than neurons. Such a being would be human in every way that matters, capable of fear and joy and the particular human genius for finding meaning even in the bleakest circumstances. It would be, in fact, a kind of immortality, a consciousness that could exist indefinitely within the shielded systems of a spacecraft, never aging, never truly dying unless the vessel itself was destroyed. There are ethical troubles here that shimmer like heat waves above summer asphalt. Would such a digital mind be truly alive, or merely a simulation of life, possessed of all the appearances of consciousness, but lacking some ineffable essence? If the digital copy is made and awakens, is it the same person who was scanned, or a new person who simply inherits their memories? If both exist, the original on Earth and the digital wanderer aboard the starship, then which one is the real continuation of the person? These are not idle philosophical puzzles. They are questions that would determine whether we are sending an explorer or creating a new being, shaping its fate to serve purposes it never agreed to. And yet, perhaps the explorer sent into space cares little about such distinctions. Perhaps the joy of discovery, the privilege of being the first to witness another world, would be sufficient recompense. What becomes clear, as we contemplate these alternatives to human spaceflight, is that we have many paths forward. Each one carries its own weight of advantage and difficulty, its own philosophical freight. A simple robot probe, hardened and clever, but not truly conscious, could reach another star and report back, asking nothing but power and the occasional course correction signal. An artificial intelligence, designed and trained specifically for the task, could perhaps accomplish far more, adapting, learning, making creative decisions, though the nature of its experience would remain forever opaque to us. A digital human consciousness, if such a thing could ever be achieved, would be the closest cousin to genuine exploration we could offer, a person in all the ways that matter, even if that person existed in a realm we struggle to imagine. And perhaps this is the genuine path forward, not the abandonment of the dream of reaching other stars, but its transformation into something that asks less of our fragile bodies and more of our ingenuity, our technology, our willingness to send our understanding outward on wings of light and electricity and mathematics, the stars would still be reached after all, still explored, still known. The only difference would be in who or what does the reaching. And so we arrive at a threshold that may define not the destination, but the journey itself. The question of whether humanity will ever reach another star begins to transform, in the quiet hours of contemplation, into something deeper and perhaps more honest. Not whether we can, but what it means that we try. There is a particular kind of beauty in reaching itself, in the act of extending our hands toward the infinite, even while knowing those hands may never close around what they seek. The Voyager probes, now traveling beyond the edge of everything we recognize as home, carrying golden records with sounds and images of Earth, were never meant to find another world. They were meant to try. They were meant to represent that fundamental human gesture, the reaching outward that defines us as a species more surely than our intelligence or our capacity to build. Consider the starlight that has reached your eyes tonight, light that departed its source before your ancestors learned to walk upright. That ancient photon, traveling faster than anything we can propel ourselves to, still required years or centuries or millennia to arrive at this small blue planet. And yet it came. The universe permits light to cross the voids. It permits even the slowest, heaviest, clumsiest travelers, creatures made of water and calcium and carbon, to understand that light, to trace its origin, to wonder what lies where that light was born. There may be wisdom in that incompleteness, in a cosmos where we might theoretically reach the stars, but likely will not. We find ourselves in a peculiar and perhaps perfect position, not abandoned to our planetary cradle, not triumphantly settled across 1,000 worlds, but reaching, building, imagining and designing and launching smaller and faster and cleverer vessels than yesterday's, forever in the act of becoming interstellar, even if the final threshold remains just beyond. The generation ships we imagined, with their descendants born and dying between worlds, need never be built for their dream to matter. The frozen sleepers in their chambers of dreamless suspension, waiting for worlds that may never come into view, exist as a kind of poetry about our stubborn refusal to accept limitations. The laser-pushed nanocraft, so small and strange and beautiful in their audacity, will carry forward our curiosity even if they carry only instruments and not flesh, even if they carry only the idea of us. Think of what we have already accomplished in just the last handful of centuries. We have built machines that touch other worlds. We have sent our words traveling at light speed itself, and they arrive almost instantaneously across distances that once would have meant the permanent severing of all connection. We have captured images from the edge of the universe and studied the light of stars being born and dying in the ancient past. We have decoded the very instructions written into our own bodies. We have done so much in such a brief span of time, with technology still in its infancy. Perhaps the true marvel is not that we will struggle to reach the nearest star, but that we will keep trying anyway, that each generation will inherit the reaching from the previous one and add their own effort to it, their own innovation, their own dreams translated into mathematics and metal. Some of the children sleeping now will grow to adulthood and dedicate their lives to this impossible journey. Some of them will solve problems we cannot yet articulate. Some of them will see further than we can see, will imagine routes we have not dreamed of. The stars will remain distant. The speed of light will remain inviolable, a law written into the deepest fabric of existence itself. The fuel masses will continue to multiply with each increase in velocity. The void will continue to wait with its radiation and its dust, and time itself will continue to play its subtle tricks on travelers far from home. These obstacles do not diminish with wishing. nor do they yield to determination alone. But what matters in this moment, in the darkness where you rest, is that we know about them, that we understand them, that we have calculated the price and we contemplate it anyway. That somewhere in the world right now, someone is working on the problem. Someone is writing equations on a paper or a screen. Someone is building something small that might become something larger. Someone is asking the question that will lead to the next answer. This is what reaching means. It is not arrival. It is the eternal forward movement, the stretching of the hand, the launching of the vessel, the transmission of the signal into the dark, hoping for a reply that will not come in our lifetimes. It is the knowledge that our best efforts may only be the first steps of a journey that will require thousands of years. It is the grace of accepting that we may be builders of the road that others will travel on, long after we are gone. And there is something profoundly restful in that thought, is there not? The knowledge that you need not solve it all, that the burden is distributed across time and generations and millions of human minds working together, often unknowingly, toward a collective dream. That your small part, your tiny moment in history, contributes to something vastly larger than yourself. That you are part of a reaching that stretches backward to the first humans who looked up and wondered, and forward to people not yet born who will look up and wonder still. The stars above you will be there tomorrow night, in the same positions they have held for all of recorded history, unchanged by our efforts or our longings. They will continue to shed their light across the void without asking our permission or our achievement. They will wait, and we will continue to reach toward them, not because success is guaranteed, not because the journey is comfortable or quick, but because something in us demands it. Something in the architecture of human consciousness requires that we try. So let the thought settle gently into your mind now as you drift towards sleep. You are part of something vast. The reaching continues, with or without your wakefulness, with or without your effort, carried forward by the collective momentum of human curiosity and courage. The stars may never be your destination, but the reaching toward them, the journey of understanding why they remain beyond, the slow accumulation of knowledge across centuries that is happening now, that is real. And in that reaching, there is a kind of arrival all its own,